High-sulfide gold ore presents a specific metallurgical challenge. In these deposits, 20 to 30% of the gold is locked inside sulfides, primarily pyrite. Because the gold is encased within these rigid metallic structures, standard extraction chemicals cannot physically make contact with the gold particles. Attempting to process this raw rock using a standard direct cyanide leaching circuit results in the chemicals washing over the pyrite armor, leaving the gold untouched. This data compares standard ore to high-sulfide ore. On the left, standard ore delivers high gold yield for low chemical cost. On the right, high-sulfide yield drops significantly while chemical cost surges, as leaching agents are wasted on the host rock. Applying direct leaching to this ore will exhaust the operational budget while producing very low recovery. Because direct leaching is ineffective, operators must evaluate specialized alternative processing plants designed to separate the gold from the sulfide matrix. The decision depends on how much capital and operational complexity an operator is willing to deploy to access those encased gold particles. Selecting an extraction method requires balancing the potential return on investment against the complexity and capital requirements of the plant. This chart evaluates extraction methods by plotting the required operational complexity against the metallurgical yield. In the lower left quadrant, gravity separation serves as the baseline. It provides an 85% recovery rate and a 54.9 gram per ton grade. This method uses a centrifugal concentrator to spin the crushed material, which separates heavier gold particles and removes the waste slime. It requires very little energy to operate and occupies a small physical footprint on the site. The trade-off is that the centrifuge cannot catch the finest encapsulated particles, meaning up to 15% of the gold is lost to the tailings pile. Gravity separation illustrates that low operational costs come at the direct expense of maximum extraction potential. To capture the gold that gravity leaves behind, the next logical step is to increase operational complexity through flotation. Moving further right on the complexity axis, sulfide suppression flotation increases the metrics to an 88% recovery at a 56.1 gram per ton grade. This method introduces chemical reagents to the slurry to suppress the waste sulfides while allowing the gold to float to the surface for collection. The circuit requires a 3-stage process, 1 roughing stage followed by 2 concentrating stages. This achieves a higher recovery than gravity, but it requires much stricter chemical management and process control. For operators who prioritize absolute yield, the third method is mixed flotation. Mixed flotation reaches the highest point on the yield axis at 93.08% recovery, though it shifts significantly to the right in complexity. This requires a highly complex circuit of coarse grinding, a mixed flotation stage, secondary fine regrinding, and a final flotation stage. This secondary phase requires careful particle size control to free the trapped gold without overgrinding the material into an unprocessable powder. Achieving a 93% recovery requires high grinding energy costs and a vast expanded plant footprint to house the additional mills. Flotation trades mechanical simplicity for intense energy consumption to gain a single-digit increase in recovery percentage. There is a final option for operations that prioritize the highest concentrate grade over total recovery. At the extreme far right, Flotation Roasting Cyanidation sees total recovery drop slightly to 89%, but the grade jumps to 76.25 grams per ton. The process begins by enriching the ore via flotation, then mixing that concentrate with slaked lime and specific additives. The mixture is heated to 650 degrees Celsius, a process which completely destroys the rigid sulfide structures that encase the gold. This creates a highly porous roasted sand, with the gold particles finally exposed for extraction. The roasted sand is then mixed at a specific solid-liquid ratio and leached with cyanide. The operational costs are high, including the thermal energy required to maintain a 650-degree roaster and the management of toxic cyanide on site. Because of the high heat emissions and the use of cyanide, this method faces the most difficult environmental permitting hurdles in the industry. Roasting exposes encased gold to provide a premium-grade concentrate, but the capital and regulatory burdens limit its use to specific jurisdictions. The correct method depends on your scale and regulatory environment. This decision tree maps out the options, starting with your available capital. Consider a junior operator with limited upfront capital. The low capital branch leads directly to gravity separation. Accepting a 15% loss to the tailings is a necessary trade-off to avoid the cost of heavy grinding mills and complex chemical circuits. For operators with high capital to deploy, the tree reaches a decision point between prioritizing concentrate grade or total recovery. An efficiency optimizer focuses on total volume and leaving as little gold as possible in the ground. Prioritizing total recovery leads to mixed flotation. A 93% recovery offers the highest extraction, provided the operation supports the energy costs of intensive grinding. For major operators chasing premium grades, the final check is the regulatory environment. If you can permit a roasting facility, flotation roasting cyanidation is ideal. Do not overcapitalize a processing plant if the volume of the ore body cannot support the complexity of the circuit. Operators should send samples to a qualified metallurgical lab for extraction tests before purchasing equipment.